Good afternoon, good morning to everyone. And well, first of all, I should like to review the content of the previous lecture and the present lecture that you are supposed to see on a video. So I will start with sharing my screen now. You probably remember that the previous lecture was dedicated to light coherence, and well, some of us could have a misconception about what the light coherence is, just thinking that it may only happen with a laser light, But as we have seen during the previous lecture and the present one, quasi-monochromatic light, could also lead, to some degree of light coherence, So just as a reminder, we started first with a two-hole Young's experiment where we considered monochromatic light. And then where there was a screen with two pinholes, and we were looking in the observer screen the distribution of light, which consisted in a series of bright and dark fringes. Then last time we saw that, well, if we would not consider just monochromatic light, but quasi-monochromatic light, it means light emitted with the frequencies near a central frequency within a certain bandwidth, so nu plus or minus delta nu. So I will just zoom here on it to see little bandwidths. And if we were looking in a screen, well, we would still see the interference of fringes here. The reason is that the electromagnetic field can then be represented by the following expression. Well, it's still an oscillation with a frequency nu, but the amplitude is being modulated, and the amplitude is modulated with a frequency which is much slower, which is delta nu, the bandwidth frequency. And we can see here, there is an illustration of combining different trains of waves with frequencies very near to each other. And the resulting train of waves is still the train of wave with a frequency nu, but with its amplitude being modulated. And the period of modulation is 1 over delta nu, where delta nu is bandwidth. Now, if you represent the variation of the electromagnetic field, not as a function of time, but as a function of distance, but now the length of the modulation on the z-axis is what is known as a coherence length. And the coherence length is kind of effective wavelength, which is lambda squared divided by delta lambda. So we see it here on this diagram that it's much broader than just one single wavelength, represented by the separation between these two arrows. Okay, now I try to zoom this one. Then we wondered, in presence of quasi-monochromatic light, what would be the distribution of light in the screen? And well, the final expression we came to is the following. So we'll just highlight the result. So the intensity distribution is well, the distribution due to each single aperture, but then there is an interference terms here. And we see that in presence of quasi-monochromatic light, this is a module of the complex degree of mutual coherence, is not equal to 1, which would be the case in case of a pure monochromatic light, but it depends on the correlation between the electric fields at the two pinholes. So it's called the complex degree of mutual coherence. Now, last time I mentioned that if you multiply the time delay between the arrival, yeah, of the two beams in the observer screen by the light velocity, yeah. This would be equal, yeah, either sometime for a bright fringe to an integer number of wavelengths, or if you have a minimum, yeah, to odd number of half wavelengths, yeah. And it's possible, yeah, to represent this not as a function of tau, this time delay, but as a function of x, yeah, the x-axis coordinate. Yeah. Now, from this expression, we saw that if we define, yeah, an objective measure to measure the contrast of the fringes, which is known as the visibility, being the difference between I max, I mean, and divided by the summation of the two, we would find that the visibility, yeah, is just exactly equal to the module of the complex degree of mutual coherence. So this is a very important result. Yeah, we don't know yet physically what represents, yeah, the complex degree of mutual coherence, but we know that it's possible to get it from the measurement of the contrast of the fringe, defined as being the visibility. Okay, now I move to the next slide. Yeah, and well, the next slide is about the present lecture. Yeah, the one you visualize on YouTube. Yeah, it's about spatial coherence, phase coherence. Yeah, so yeah, the subject, yeah, of the present lecture, yeah, is the following. We will just zoom a little bit here. Yeah, well, we would like to evaluate, yeah, what is the complex degree of mutual coherence, which is defined by this present expression. So V1 of T represents, yeah, the electromagnetic field, yeah. Well, for this pinhole, V2, yeah, the electromagnetic field, yeah, at the second pinhole. Then we take the time average, we conjugate complex the first electromagnetic field, divide by the intensity, yeah. And what we find, well, is that the electromagnetic field at any of this pinhole, yeah, is of course equal, yeah, to the contribution of all the electromagnetic field due to small projected, yeah, surface elements, yeah, on the sky. So of course the distance, yeah, is absolutely very far away, yeah, from the screen. Yeah, this is just for visualization purpose that we set, yeah, the source so close to the screen. Okay. So now the demonstration, yeah, is shown in the lecture notes, also in the YouTube presentation, and the result, yeah, is the following. Yeah, it results in the Zernikovic Theorem, yeah, which I highlight here, and which is valid under one hypothesis, one big assumption, yeah, is that the difference between the lengths from one given source element to the two single apertures in the screen must be smaller than the coherence length that I defined previously. So it's the square of the wavelengths divided by the bandwidth, yeah, expressed in a wavelength units. So if this is satisfied, yeah, you get what is known as the expression, yeah, this is the Zernikovic Theorem, is that the complex degree of mutual coherence is equal to a double integration of the distribution of the intensity over the source, divided by the square of the distance between the source and the screen, and then you have this complex exponentiation function, yeah, which comes into play. Now, astronomers only observe very, very distant objects, yeah, and this leads to a very nice simplification, which is known as a Fraunhofer Approximation, yeah. So we assume, and maybe, yeah, I will just go a little bit below, yeah, on this image. We just assume, yeah, that the physical size of the source or the distance between the two apertures, yeah, which form your interferometer, are much smaller than the distance between the source and the observer. Yeah? And this is a very good approximation, of course, yeah, because when you have very compact source, yeah, it may have the size of a star here. Here, well, the largest distances we've seen, yeah, is probably less than 1 kilometer compared to many, many light years, yeah, very often hundreds or thousands or even more light years between the source and the screen. And now when you particularize, yeah, the Zernikovic theorem, yeah, within the Fraunhofer approximation, you end up, yeah, with this very nice result, yeah, that the complex degree of mutual coherence, well, is just equal, yeah, to this expression, which is a Fourier transform, yeah, of the distribution of the normalized intensity distribution of the source, yeah, projected, yeah, perpendicularly to the line of sight, yeah. Well, here there is a annoying, yeah, instrumental factor which does only depend, yeah, on your telescope and their distances, yeah, and it's possible to get rid of it, yeah, and I'll come to that, yeah, later on, yeah, maybe in 3 or 4 lessons, yeah, how can you get rid of this annoying factor, which is a phase factor, just, yeah, and which can be corrected, yeah, as I'll explain to you later. So now I jump to the next slide. And perhaps to make it more visible, I will just load another presentation here. Just a moment. I go in my document. And I just prepared this summary of very important formula, which will be very useful for you. Yeah. So this is after lecture 2A, which was the first lesson dedicated to light coherence. Yeah. So the first expression, yeah, of the complex degree of mutual coherence, yeah, as I said, is the time average, yeah, of these two products divided by I, which is the intensity given by one of the two apertures. Yeah. Then we have seen that provided that the time delay between the arrival, yeah, of the two light beams into the observer screen is smaller than the coherence time given by 1/delta nu, we could rewrite the expression of the complex degree of mutual coherence in this form. Yeah? So it's a module calculated for tau equals 0. Here there is a complex exponentiation, it's a phase factor. And then here is a time dependence, yeah, which just depend essentially on the time delay. Okay, now if I particularize this expression for tau equals 0, from this equation 2, you get equation 3 because this one is equal to 1. Now, if you take the real part, yeah, of that equation 2, you obtain that it's the module of this, and the real part, yeah, of the product of these two complex exponentiation, yeah, is just a cosine. Yeah? And now I just remind you that the distribution of the light intensity in the screen when you have the two holes working in quasi-monochromatic light, yeah, was given by this expression, yeah, and this is the final result. Now, as I said, yeah, c times tau is equal to, in fact, one of the previous equations. I think it was equation number 17, which is n times the number of wavelengths, which is also x. So this x coordinates in the observer screen. B is a baseline between the two holes, and z is a distance, yeah, between the two holes, yeah, and the observer screen. And if you, well, just insert this expression into this one, you end up with this representation of the distribution of light, yeah, in the observer screen. And we see that the visibility, yeah, is equal to the module of the complex degree of mutual coherence. Now I have a small video I can show you. Well, this video was made using GeoGebra. It is an open source, yeah, well, software, which is very nice because I've been using it for a few weeks now, even almost a few months, and I'm so delighted, yeah. So what it represents, yeah? Here is the observer screen, yeah? The x coordinates, yeah, is along this axis. The y-axis is perpendicular into the horizontal plane, and the z-axis represents, yeah, the intensity in the observer screen. So you see it's 2 times 1 plus gamma, where gamma is in fact the module of the complex degree of mutual coherence times the cosine, yeah, of the function which depends on x. And you just see here if it can work. It doesn't seem, oh yeah, it works. So it is very slow. So you see, what I'm doing here, I'm just changing, yeah, the strength of the module of the complex degree of mutual coherence. And when gamma is equal to 0, no fringes. And when gamma goes, yeah, very near to 1, yeah, I have a maximum contrast in the fringes, yeah. And you see the fringes, yeah, from all the sides, yeah. And well, I just encourage you, yeah, to download, yeah, this open source software, yeah, which is called GeoGebra, yeah. It's very, very nice to make simulations and to illustrate various considerations. Now I come, yeah, as a summary of the present lecture. I also zoom on the very important, yeah, formula that we have established, which are the following. So we have calculated, yeah, for an extended source this time, not anymore a point-like source, yeah, what is expression, yeah, of the complex degree of mutual coherence. And we just saw that we were interested by the case when tau is equal to 0. And we found by applying the Zernikovic theorem within the Fraunhofer approximation, yeah, that it is just equal, yeah, to the Fourier transform. Yeah, so here is a Fourier transform, yeah, of the distribution of the normalized intensity of the source in the sky. Yeah, and now you see here that you have 2 variables, u and v, and u and v are equal to x. X, yeah, is a position, yeah, along the x-axis of one of the 2 apertures, one of the 2 pinholes with respect to the first one. Yeah? Y is the position of that second aperture with respect to the first one, but along the y direction. Yeah? So xy represent, in fact, on the ground, yeah, the horizontal plane, and we divide it by lambda. And this results in the uv quantity. Yeah? So what does it represent, yeah, physically? Yeah? Well, these are, in fact, angular scale frequencies. Yeah? So I explained to you why, yeah, these can be called frequencies, or in the literature, they are referred to as space frequencies. Yeah? Okay, to do that, yeah, I take my pen and try to do very small demonstration. So let's assume that, yeah, we have a sound, yeah, with a period t, yeah. So t is a period, yeah, of the sound, yeah. So we know that if we take the inverse, yeah, of t, so 1 over t, yeah, this is known as a frequency. You agree? It's a time frequencies, yeah. Okay, now if I take, you remember lambda over b. So I do it once more, not easy to work on the screen. Lambda over b, where lambda is a wavelength, yeah, and b is a baseline. We know that this quantity, yeah, represents a kind of angular resolution, yeah. So it is an angle, kind of angular measure of something, yeah. In our case, lambda over b, if b is a baseline, yeah, would be twice the angular resolution, yeah, of the interferometer. Yeah. So if you take the inverse, yeah, of lambda over b, well, this results in b over lambda, yeah. And since I took the inverse, I may call it, yeah, just a frequency. And it's a frequency of an angular scale, yeah, or of an angular space, yeah. So this is what represents u and v, x over lambda, y over lambda. X is the baseline along the x-axis, y is the baseline along the y-axis, yeah. And if you divide by lambda, yeah, this is just like a baseline divided by lambda. So it's an angular space frequency. Yeah. And so you see what you obtain here by taking the Fourier transform, yeah, of the distribution of the normalized specific intensity over the source, yeah, is a complex degree of mutual coherence, yeah, as a function of these two angular space frequencies. So two space frequencies. Yeah. So now the normalized distribution intensity of the source, what is it? Well, it's just the intensity, yeah, at a given position divided by the integrated intensity over the whole source. Yeah. So that if you would integrate this one over the extent of the source, you would find it equal to 1. Yeah. And therefore, yeah, it is known as a normalized intensity distribution of the source. And I remind you that all of this is true as long as the length difference between two beams coming from one source element to the two aperture of your interferometer is less than the coherence length. Yeah. Okay. Now, well, I think this will be explained to you by Dash during one of his next lecture. Yeah, is that if you take the inverse Fourier transform of this quantity, yeah, well, you just recover the distribution intensity of the source, yeah, well, which is normalized, of course, yeah, and well, I think during the coming lectures, we will play with all these concepts of Fourier transform, yeah, and I think I will just jump now to the previous set of yeah. So I come back here to the present lecture. Yeah, where I just outlined in the lecture notes and in the video as well some remarkable properties of the Fourier transform. Yeah. So this is just expression of a Fourier transform in one dimension. Yeah. So of the function fx. Yeah. So you multiply by exponential minus 2i pi sx, integrate over the variable s, x, and you see that this is a function of s. Yeah. And indeed, this is the definition of the Fourier transform of the function in one dimension of the variable s, which is real. Now the inverse Fourier transform well, is given by this expression. So you see that you may recover the function fx if you know the value of its Fourier transform as a function of the variable s. Now, I just raise. And well, usually the inverse Fourier transform exists where under the assumption, well, necessary condition is that f, the function, should be of summable square. Yeah. So this integral should exist. Now, next page. Yeah. You may define, of course, the Fourier transform in a multidimensional space. Yeah. And well, it's what came up with representation of the complex degree of mutual coherence. You saw that it was a double integration over the plane of the sky. So the variable was zeta and eta, which were angular scales, space angular scales. Yeah. Now, nice properties of the Fourier transform are first the linearity. So if you multiply a function by the constant a, well, the Fourier transform of a times f is equal to a times the Fourier transform of f. Now the Fourier transform of the summation of two functions is just the summation of the two Fourier transform. Yeah. Then about symmetry and parity, the only thing important I would say here, yeah, and this you may try to demonstrate it yourself, yeah, is that if the function fx, yeah, is symmetric, yeah, so if it is an even function, so f of minus x is equal to f of x, yeah, you will find out that the Fourier transform of that function, yeah, is real, yeah. So there is no complex, doesn't need a complex representation, yeah. So this is a very important property because when we will consider in the sky, yeah, symmetrically distribution, well, symmetrically intensity distribution, like the disk of a star, yeah, or two stars, you know, which are equally bright, or anything symmetric, where the Fourier transform, yeah, will always be a real function. Yeah. Now, another important property, yeah, is a similarity property. Yeah. Namely, that the Fourier transform of a function which depends on x divided by the real constant a. Well, the Fourier transform is a function of the real variable s, of course, but it's very easy to show that it's equal to the modulo of the real constant multiplied by the Fourier transform of the function fx, but not as a function of the variable s, but as a function of the variable s multiplied by the real constant a. Well, all these demonstrations, yeah, have been made, yeah, I think in the, well, some at least, yeah, in the YouTube video, yeah. Another very important property of the Fourier transform that we will be using in the future, yeah, is a translation property. Namely, that if you translate the function, yeah, in the original space, yeah, in the Fourier space, it corresponds to a rotation. Yeah. So you see, if a, yeah, is a real constant, yeah, the Fourier transform of the translated function is this complex exponentiation function, where you have here a and variable s multiplied, yeah, by the Fourier transform of the original function. Yeah. Now, a very important, yeah, result also is the following, but the demonstration is given, yeah, in the YouTube presentation, is that it's a door function or the window function, or, well, it has many different names. So it is a function which is square. So you see it here, square function, which is equal to 1 if the modulo of x, yeah, is smaller than 1/2, yeah, and 0, yeah, if it is larger. Yeah. And now the Fourier transform, yeah, of this down function, yeah, is just the sign cardinal, yeah, which is a sine of pi, the constant pi multiplied by s divided by pi s. Yeah. Now, well, if you want to apply the similarity relation, yeah, so if you say, okay, but my door function now depends on x over a, we know that then it's the modulo of a multiplied by the sink of the variable s, but this time multiplied by the real quantity. And here we see a representation. Now, still one very important, I think, result, yeah, is the following. Yeah. Yeah, well, this I may try, yeah, with my pen to do it here. We will see if it works. So I just try to, yeah, select larger widths. Yeah. Let's assume, yeah, that I want to calculate, yeah, what I want to calculate, the Fourier transform, of the Dirac function, like this, yeah, which depends, of course, on the variable s. So you would say, okay, this is equal to, I would change the color, yeah, maybe I can colorize now, yeah, but it will be equal to the integration, well, from this one, I will just, yeah, move it somewhere else, just like that, yeah. it's equal to the integration. Oh, it doesn't work anymore, so I have to set it back. Oops. Yeah. So it's. So I'm just discovering this tool. Oh, no, it's not what I want. So is it integration? No, it doesn't work. Integration from minus infinity to plus infinity, yeah, of, you would say, the direct function multiplied by exponentiation, yeah, of minus I to pi s times dx. Okay. Now we know that when you take the integration of delta x times any other function, the result will be the value of this function for x equals 0, but the exponentiation, yeah, of, oh, here there is an x missing, yeah. Here I forgot to multiply by x, yeah. If you take this for x equals 0, it will be equal to 1, yeah. So the Fourier transform of the direct function is equal to 1, in fact, yeah. Yeah. Which means that the inverse Fourier transform, yeah, the inverse Fourier transform of 1, which is given by this expression, yeah, is equal to the direct function itself. Yeah? So you may just, well, you may just go back, yeah, to this demonstration, you know, when you will be, what, this I just take away, yeah. When you will have some time, but well, it's very obvious, yeah. So this result is very obvious, and then there will be some exercise, yeah, proposed, yeah, for the next lecture. But I think I will stop here now, and would like to hear about you, yeah, your questions, your worries, yeah. But all of this, yeah, is very simple, yeah. So I come back to here to you.
All right, thank you, Jean.
Yeah.
Okay, now if you guys can ask questions, just raise your hand, I'll unmute you.
Yeah.
Or if
yeah,
your
so,
mic doesn't
yeah.
work, you can always type in the chat.
Yeah, so all these concepts, yeah, are very simple. You will see, you know, you have to just go back, yeah, to the definition of the Fourier transform, yeah, and then start, you know, with very simple properties, yeah, and then you will get, you know, the practice, and it will become, you know, a very easy exercise, especially following the lectures, yeah, on Fourier transform, which will be given in addition, yeah, on each Wednesday, yeah, by Daesh, yeah. So, is there any question?
There's only one in the chat which says, can you describe symmetry and parity again?
So if I can describe what, can you?
Symmetry and parity. Properties of the Fourier transform.
Yeah, symmetry and parity, yeah. Yeah, maybe to do that, I will go back to, I try to go back to the screen, yeah, okay?
Sure, yeah.
Yeah. So this is desktop open board. Okay, do you see open board now? Yes,
yeah.
I guess so. Yeah. Now, my problem here, yeah, is that I don't know how to, but it will work. Just a moment. Yeah, I just come back to parities. Yeah. So here are some remarkable properties. Here are just try to find where symmetry and parity. Yeah. Well, so this is just highlighted here in the lecture notes. Yeah. Well, a function, yeah, can be represented as a summation of two functions. One which is its even part, and the other one which is its odd part. So P of minus x will be equal to P of x, and I of minus x will be equal to minus I of x. So any function can be represented by this expression. Now, if you'd like to get convinced about that, you just write f of x, then f of minus x, then you will find that it's equal to P of x minus I of x. Then either you can co-add the two lines or subtract them, and you will find that indeed any function can always be represented as a summation of an even and odd part. Now, if you insert this representation of the function in the definition of the Fourier transform, well, you'd find that that it is the integration from minus infinity to infinity of f(x) multiplied by the complex representation of the exponentiation function. But this one, you just say, well, E, so I'll just write it down. Whoops. So I have a pencil here. Now I choose color here, the size here, and I try to write it here. Okay, down. Now you may, the problem. No. Oh, it does anything yet. No, it doesn't work. It doesn't matter. But the function e of ix, e with exponent ix, is equal to cosine of x plus I times sine x, right? So in the Fourier transform, what you do, you represent the complex exponentiation as a summation of cosine plus I times the sine of the correct argument. And then you find that it may be represented as follows. So this is the resulting expression. Now, if you think that fx is just an even function, it means that I of x is equal to 0. But if I of x is equal to 0, this imaginary part doesn't exist. It's equal to 0. So what remains is this contribution. And you see that it depends on the variable s, but the cosine of minus s is equal to the cosine of s. So you see that this is an even function, as a function of s, and the Fourier transform exactly the same. So which means that when we will consider in the sky symmetrically distributed intensities, like a star which could be a square, or the star which could be a disk, this is a centrosymmetric, well, the Fourier transform in 2 dimensions would always be a real expression. So this is what I was saying. Okay. So to erase is easy. So is there any other question now? Or is it okay, sufficient, or do you need more explanation on this?
We'll see if they have a follow-up. But the other question is, what is the mechanism of formation of images from the interference fringes?
Oh, okay. Now I have to share my screen again. So I shall share screen. Come back here. I come back on the previous slides. Previous result. So this is the Zernikovic theorem, or maybe the other presentation. It's more compact, and so I come here. So you see, we have established, during the present lecture, so you have to look at the at the video, of course, yeah, that the expression of the complex degree of mutual coherence, yeah, is equal, yeah, to the Fourier transform, yeah, of the normalized intensity distribution, yeah, of the source you are looking at, yeah, and it's a function of the frequencies uv, yeah. So let's assume that v equal to 0 and u is equal to b, the baseline, yeah. So of course you would have an interferometer with two apertures, yeah, uh, yeah, position along the x-axis, yeah. So the distance between your two apertures, yeah, is equal to b. And what you would do, you would look at the star, and you would see some fringes, yeah. So what you would measure the module, yeah, of this quantity, yeah, and this would be in fact the visibility of the fringes, yeah. So if the source is not resolved, yeah, you would see that the module of this quantity is equal to 1. If the source is resolved, you would see that it's equal to 0. And it's in between, you get an intermediate value. Yeah. Now, the idea would be that, well, you do this measurement for different baselines, yeah, different values of the baseline, okay? And you get a set of measurements. Okay, that's nice, yeah? Now, you may change now the orientation of your baselines, yeah? We were doing it along the x direction, now we can do it along the y direction, but we can do it along any direction and changing your baselines, yeah? So you get, you're covering, yeah, the UV planes, yeah, with measurements. And let's assume that you get a very nice set of measurement, yeah, of the fringe visibilities, yeah, the contrast of the fringes. Yeah? So what you would do, you'd put into this expression, yeah, all those values that have been measured, and by taking the inverse Fourier transform, you get, yeah, the real distribution, well, normalized, yeah, of the source intensity, but with the resolution, angular resolution, yeah, which is that of your interferometer. So it's a lambda over b, or lambda over x, or lambda over y, yeah. So if the baselines, yeah, is of several hundred meters, yeah, you get angular resolutions of milli-arcsecond, yeah. So you see that you would be able to reconstruct, yeah, the source distribution of the object just from the measurements of the visibilities of the fringes, yeah. And this is what is called, if you can do that, this is called aperture synthesis, yeah. And this is commonly made, yeah, with the VLA, with the GMRT, yeah. And now, well, people are starting doing it, you know, with optical interferometer. Now, let's assume, and this will be shown in the exercise, yeah, that, well, you don't have many baselines measurements, yeah, because maybe you have just two aperture and a fixed baseline, yeah. Well, would you be able still to do some science with it? Yes. If you have some a priori knowledge, yeah, on the model which represent your source. For instance, you could say, oh, I know from spectroscopy, yeah, that the source I'm looking at can consist of a binary star, yeah. But what you don't know is what is angular separation. You don't know what is orientation. You don't know what is a flux ratio. So three unknowns, yeah. So with very few visibilities, yeah. So with very few baselines, yeah, maybe 3 or 4 different baselines, you would measure the contrast of the fringes, yeah, and you would be able, yeah, really to find out, yeah, what is orientation, what is angular separation, and what is the flux ratio of the two stars that you cannot resolve with a single aperture, but that you are resolving with your interferometer, yeah. So if you are able, yeah, to make many measurements, yeah, of fringe visibilities, yeah, because you have many different baselines possible with different lengths, with different orientations, then you will be able to cover the UV space. And by just taking the inverse Fourier transform, yeah, of this quantity, you will recover, yeah, an image of your source, yeah. But you need good UV coverage. Yeah? If you just have a few measurements, then a priori knowledge, yeah, of the model which represents the distribution of light intensity of your source, yeah, may give you very good clues. Yeah. Now, what I would like still to add, yeah, is the following. Yeah. that thanks to the rotation of the Earth, yeah, well, the source looks at your interferometer, and what it sees the baseline, yeah, changing its orientation as a function of time, and even its length, because it's a projected baseline, yeah. So thanks to the rotation of the Earth, yeah, they're getting, yeah, a series of measurements, yeah, for different space frequencies, yeah. And so you're starting covering, yeah, the UV plane, yeah, what is known as the UV plane. Now, if you have many different apertures, yeah, well, you have many different independent interferometers, yeah, and then it's very easy to get a very good coverage of the UV plane, yeah. And this is what is achieved, you know, with ALAMA, yeah. I think there are about 60 apertures, yeah. So the number of independent interferometers, yeah, well, is number of pairs, well, number of combinations, yeah, of pairs of telescopes among 60 apertures. So it is 60 times 59 divided by 2, yeah. So 30 times 59, well, it's about 1,800, yeah, measurements, yeah, in 1 minute, yeah. So then you get a very good coverage of the UV plane, and you are able, yeah, directly, yeah, to get model independent images, yeah. But most of the time, well, with optical, yeah, interferometers, yeah, the number of aperture is limited, yeah. Uh, I think the, the most sophisticated ones in terms of the number of apertures, yeah, is the one in Pasadena, yeah, and it has 6 apertures, yeah, which means that in a single minute, yeah, they're able to get 15 visibilities, yeah. Well, for VLTI, yeah, you only have 4 independent apertures, well, 4 apertures, yeah, which means that you get 6 independent measurements of a complex degree of mutual coherence, well, namely the module, but you may also take advantage, yeah, of the phases, and we'll come to that, yeah, later. Now it's still too early, and then you may proceed, yeah, with this inverse Fourier transform, yeah, and get directly, yeah, an image of what you're looking at, and that you don't know what it is, yeah. So if you have already a good a priori of what your source is, yeah, then it's very easy. As another example, yeah, I may tell you the following, yeah. With a single measurement, with just one single baseline, yeah, looking at a star, and you'd like to measure its angular diameter, yeah. In principle, just one single measurement would allow you to measure the angular diameter, because you have some a priori knowledge, yeah. You know that it is a star. Well, it's not a jet, yeah. It's not well, something more complex. So it's circular symmetry, and it has just a certain diameter, yeah. So with just one baseline, you may derive immediately an angular diameter, and if you know the bolometric flux, yeah, get a very good estimate, yeah, of the effective temperature of the star, yeah. So, I mean, well, you will see during the coming lecture, yeah, it's a very rich field, yeah, and you can do very interesting things, yeah, with the interferometers. Okay, maybe now I stop showing my screen, come back to you to see whether there are more questions.
Yeah, there is one of the question from Nikita Rawat is, can you please explain why we consider the expression is the path length difference is much less than the coherence length?
Why we do that? Yeah.
Yes. What is a physical interpretation of this?
Yeah. So let's go back. Sure, my
Equation 40. It says,
I go to the screen. Yeah. So to do that, to explain, I have to load the other presentation. I don't know exactly which page, but we'll find out here. 13. 18, yeah, probably it's about here. Yeah. So this is the subject, yeah, of the present lesson, yeah. So just have a look, yeah, at the YouTube presentation, yeah, and you will see exactly why. So we were interested, yeah, in evaluating, yeah, this expression, yeah. What is a representation, yeah, of the complex degree of mutual covariance? And we knew that, well, it is a time average, yeah, of the product of these two quantities, where V1, V2, yeah, is our expression of the electromagnetic field, yeah, and the two single apertures, 1 and 2, yeah, divided by I. So, well, I just lift up a bit this presentation. Yeah. To do that, we say, well, V1 and V2 can be represented as a summation, yeah, of each elementary contribution due to each single surface element, yeah, at the source. So you see the source, yeah, is decomposed, yeah, into n elements, surface elements, infinitesimal, yeah. And what we say, well, we just say the following, yeah. Oops. Just say, okay, in this expression, yeah, we insert V1, we insert V2, we take the conjugate complex of this expression, and when we multiply, yeah, well, we have many cross products, yeah. And so the cross products, yeah, are shown here. There are cross products here, where one summation is over the same element, I, yeah, of the light arriving at aperture 1 and 2. And the second summation, yeah, is for I different from J. It means that you're considering, yeah, two different source elements which emit light in an incoherent way, yeah, which means that there would be no interference possible between the light. So on average, this term would be equal to 0, yeah. So what is left over, yeah, is just this contribution, yeah. Okay. Now, V1I, yeah, and it's the same for VI2, yeah, can be represented as follows. Well, this is a real amplitude of the electric field, yeah, but not evaluated at time t, but at a time t minus the distance between the first aperture and the surface element I, divided by c, because this is the time it will take for the light, yeah, to come from surface element I to aperture 1, yeah, okay? And you do the same, yeah, for the second element. Now, what you will do, you see, you take the conjugate complex of this first expression and multiply by the second one, yeah? So we will have this quantity multiplied by the second one, okay? And now we would come to this expression, yeah? And this we could say, okay, this is valid, yeah, as long as I may multiply the conjugate complex of this expression by this second one. And I have the right to do that, yeah, provided that the value of the two amplitudes, yeah, are comparable, yeah. But I know that the value of the amplitude, yeah, of the quasi-monochromatic light, yeah, varies with the wavelength, yeah, with the wavelength, which is the coherent length, yeah. So if the difference between these two lengths, yeah, is much smaller than the coherence length, well, I know that the amplitude will be about the same, and I will have the right, yeah, to say that Ri2 here is about equal to Ri1, and since I take the conjugate complex and multiply it by this one, yeah, I would end up with the module of the square of this quantity, yeah. And this is where you need that approximation, yeah. So you need that the difference in length between the rays coming to aperture 1 and 2 from a same surface element, yeah, is less than the coherence length, yeah. Otherwise, yeah, well, the amplitude can be too different, yeah. But you remember I showed well, I tried to go back, yeah, to that transparency, which is here, yep, exactly here. to this figure, yeah, you see that if I take the amplitude at this location, or the amplitude at this location, it will be about the same, yeah? But if I take the amplitude here, and another amplitude somewhere there, I don't know what it will be. Yeah, there will be no coherence between the two. And then I don't have the right to say that AI1 conjugate complex times AI1 are the same. And this would not end up in the square module of the amplitude. Yeah. So this is the place where I need that approximation. Yeah. And well, this is very interesting because yeah, it means that if the difference in those lengths is too big, you're losing the coherence. Yeah. And now physically, when I look at a star, with a certain angular extent, and a baseline, B. So you see I have one point here and second point here separated by B. And if I see fringes, it means that, well, I'm able, to let the light interfere, and it means that I'm here inside, these train waves, So it means that the difference in their length is smaller than the coherence length, But let's assume that I find the baseline for which, I see no fringes, So I know I resolve the star. I'm resolving the star, It means that at that moment, well, the light coming from one hole maybe correspond to a location here, and the light coming from the second hole, is somewhere there, And there is no more coherence possible between these two trains of waves. You see, this is the reason. But just go back, to the video lecture, and you will understand the concept. Well, it's not easy, but it's also easy at the same time. You have to use your brain, and this is fantastic. What astronomy is for. It helps us. To get very good muscles in our brain. Okay, so maybe is there another question?
There's just one more about the geometric dilution effect. So
Yes.
it's from Sanjay. He says, please describe geometric dilution effect, why it occurs. I think he just means the 1 over r square dependence in the...
Yes, I know. Yeah, of course, in fact, if you take a source element, emanating light, and you measure, the amplitude of the electric field, very near to its surface, and let's assume, that the value is module A, so this is the amplitude, So it's the amplitude of the electric field, I'm not yet speaking about intensity, If you go, well, at the distance, so let's assume here it's the distance is 1 unit, and let's assume that we go at a distance of 100 units, Well, then the amplitude, of the electric field, would be the same A, module A, divided by the square root of 100, divided by 10, And now the intensity, would be, of course, the square, of the electromagnetic amplitude, So it would be just dilution you expect, 1 over r squared, correct, So the reason why by the square root of the distance, is because the geometric dilution for the intensity, is inversely proportional to the square of the distance, and this is the reason, Is there one more comment on that?
No, I think that's about it. I think we are past the time as well.
Yes.
So we can
now
start.
maybe I may propose I may propose an exercise for the next lecture or maybe it could be part of the quiz, I don't know is just assume that you see in the sky a star which has well, I try to sketch it here. Just a moment. Yeah. So first of all, I will take the plates here to make some drawings. Okay. I take the pen. Yeah. So let's assume, yeah, that you take a star, which can be represented as a square. Yeah, a strange square. I agree. Okay, like that. Yeah. And that the side of a square has an angular size of zeta 0. Okay, so this is the angular measure, yeah, of the side of the square. Yeah, zeta 0. So it's the linear size of the square divided by the distance. Okay. So the question is, what would, yeah, the complex degree of mutual coherence look like, or what, in fact, would the visibility, yeah, in the fringes that you would see, yeah, would look like, yeah, in terms of zeta 0, yeah. So this is a nice first possible application, yeah, exercise, yeah. So it's very easy because, well, you know, this square can be represented, yeah, as a double window function or door function, yeah. So you have all the elements, yeah, in the lecture notes, yeah, to carry out that measurement, yeah, or calculation. Yeah.
Okay, we can probably post that question in the course. Yeah.
Yeah. Yeah. Fine.
The course page,
now,
I mean, so that it's clear.
Okay. Yeah. For sure. Yeah. Now, one thing I forgot to mention here, yeah, is what is a background image. Yeah. No one asked me. Yeah. And this is interesting. Yeah. So when we visited the VLTI in Paradise, yeah. So you know there are 4 single unit telescopes, the VLT, very large telescope with a mirror of 8 meters in diameter, and this is, well, a fisheye photograph we took, yeah, of one of those telescopes, yeah. So you see how it looks like, yeah. So we are inside the dome, yeah, and here you see the mirror, 8-meter diameter, yeah, and then complex adaptive optic system, yeah, and well, secondary mirror, third, tertiary mirrors, and many more, yeah. Well, I think almost up to 20 mirrors before you get to the focus of the VLTI itself, yeah. So next week, probably, yeah, the background image will be a photograph of what the VLTI looks inside the tunnel, yeah. So the tunnel where the beams, yeah, are interfering. Okay.
Okay, sounds good.
So very nice, and talk to you next week.